Hello everyone, welcome. In this video I have this integral here. We are to integrate from 0 up to pi over 2 of this expression here, sine to the power 2025x all over sine to the power 2025x plus cos to the power 2025x dx. Now as you can see, there is no elementary technique of integration that can work on this one. Use substitution cannot work, integration by parts cannot work. And I invite you to try it out. Think about what technique you'd employ to solve this integral. But I want to let you know that there is a special property of definite integrals that we use to evaluate this one. I remember we have limits of integration here, so we have a definite integral, and therefore one property works out this integral very easily as follows. And I want to first of all explain what that property is. We call it King's rule. We're going to use what we call the King's rule. King's rule. I want to explain this first and then come and evaluate that integral. What does the King's rule say? It says that if you have a definite integral from a up to b of some function f of x dx, it says that this is exactly the same as the integral from a up to b of f of the sum of the limits of integration a plus b minus the variable of integration dx. So this is what we call King's rule. And I want to use a simple function here to try illustrate this. Let's look at this simple integral here. Suppose we have f of x being equal to x squared, right? And therefore, let's look at the integral from 1 up to 4 of f of x dx. So what is this equal to? Well, this is equal to, as you can see, the integral from 1 up to 4. You know we're saying a equals 1 and b equals 4. And f of x is equal to x squared dx. So we first evaluate the left side, which goes straight here, simple integration using power rule. So this is going to be equal to, remember we add the 1 and then divide by the result. So it's going to be x to the power 3 all over 3. And we are evaluating from 1 up to 4. Right. Now what does this mean? This means 4 to the power 3 all over 3 minus 1 to the power 3 all over 3. As you can see, this is exactly equal to 64. Denominator is the same, so I can just write 64 minus 1 all over 3. And that is 63 all over 3. And as you can see, the answer is 21. Right, so the left-hand side equals 21. That's working on this one. Now I want to try and use this in there and see what we get. Let's take this to page 2. Page 2, let me move this down. Right, now what I'm saying is, right, must move this. Okay, so what I'm saying now is we want to look at f of a plus b minus x. Remember, what we looked at is f of x. That part we evaluated, our answer is 21. Now we want to look at this part. Remember, a is 1, b equals 4. This is exactly equal to, if I move down here, f of 1 plus 4 minus x, and this is f of 5 minus x. But what is f of x? F of x is x squared, and therefore f of 5 minus x will be 5 minus x squared. So I'm going to say that expression should be equal to 5 minus x all squared. Let's simplify this. Expansion of this, that's 5 times 5, 25. 5 times minus x is minus 5x times 2, minus 10x. And then x times x would be x squared. That's what we get. So now let's evaluate the right-hand side. Let's work on this part now. So we're now saying, what do we get when we say the integral from 1 up to 4 of this expression? f of 1 plus 4, which is just 5, minus x dx. Remember, this is the same as f of the integral of from 1 up to 4 of this expression here, as you can see, equals that part there. 25 minus 10x plus x squared, and then we say dx. Again, we're going to use power rule here as follows, using power rule. So this is going to be 25 of obviously 25x, and then that will be minus, if you like, 5x squared. Remember, we add 1 to the power of 1, add 1, divide. It will be 1 plus 1, 2 into 10 is 5. X squared, remember, plus add 1 and then divide. That will be x cubed all over 3. Our limits of integration, 1 up to 4. Taking this to page 3, just to complete this, and let's see what we get. Maybe I can, yeah, I think I can try and use this space here before moving to page 3. Alright, so this is the same as 25 times 1 times 4. Remember, the upper limit is 4. And then minus 5 times 4 squared plus 4 cubed over 3 minus open brackets. Now we are going to substitute 1 in there. 25 times 1 minus 5 times 1 squared plus 1 cubed over 3. Right, let's simplify this and then we go to our integral. Right, simplifying this, what we get is the following. What we get is the following. As you can see there, what we have is 25 times 4, that's 100. 5 times 16, that's 80. Remember, 4 squared is 16 times 5 is 80. Minus 80, and then we have plus. That will be 64 over 3. Minus this part here, remember, it's 25. Minus 25 times 1 is 25. 5 times 1 is 5. So it's minus 5 there. And then we have plus 1 over 3. Remember, 1 cubed is 1. Let's remove the brackets. This is 20, as you can see. 20 plus 63 over 3 minus, what do we have here? This is 20, remember? So it'd be minus 20. And then minus 1 over 3. You can see this cancel. And what are we ending up with? 63 over 3 minus 1 over 3. You agree with me? It's actually 64, not 63. My hand there moved faster than I should have. Let me just remove this. Remember, there is a 64 there, so I don't know how the hand wrote 63. I think I subtracted before actually coming to it. I want to use my correction fluid here. Hopefully it works as fast as I am expecting. I'll come and fix that. So that's 64. This should be 64. You'll understand why it's coming to 63, because that's what we must get now. So it will be 64 minus 1 all over 3, because the denominator is the same, and this is 63 over 3, and again, yes, we're finding 21. So you can see clearly here, I'll fix that. You can see clearly here that f of x, which is x squared, evaluates to 21. F of 1 plus 4 minus x. Remember, 1 plus 4, these are limits of integration. Remember the King's rule, that's what it says. F of x from integration from a up to b of that x function is equal to that, where we add these two and then subtract the variable of integration, and we are finding the same result, 21 here. And after adding 1 and 4 and subtracting x, we evaluated that integral and we found 21 as well. Now, this is a very important tool. As you will see, it works on this integral very easily, as I will show you shortly. Let me fix this up. So this is 64, and that's 64. And then it simplifies 21. Now let's get back to our integral. There is our integral. Now, how do we apply that principle here? We're going to let this be equal to some integral I. So I'm gonna say, therefore, the integral we have now is the integral from 0 up to pi by 2 of sine power 20 25 of x divided by the integral divided by sine power 2025 of x plus cos power 2025 of x dx. We're going to let this one be equal to I. We're gonna let this be equal to I. So let me put somewhere here. I'm gonna write it this side. Let I be equal to this integral here. Let me remove therefore there. It doesn't look very nice. I'm letting I be equal to this expression, this integral here, and then I'm gonna use that technique. Which technique? We have limits of integration here, remember? So we're gonna say this should be the same as, I'm changing now, rewriting the same I. I'm gonna say therefore my new I, which is exactly the same integral as you have seen here, left and right, left and right. So I'm gonna work on the right hand side because of what I have now is f of x, which is this expression here. Limits of integration 0 to pi by 2. So the right hand side is gonna be the same as the limit, the integral from 0 up to pi by 2 of, watch this, sine, and I'm gonna use brackets now, in brackets, pi by 2 plus 0 minus x, and I'm gonna use these brackets now, 2025, and I'm gonna say this is all over. Down here it's gonna be sine of the same story, pi by 2 plus 0 minus x, 2025, and I want the bracket to come over this side, so I'm gonna use the bracket there. I can put another bracket here, it doesn't really matter. So I'm gonna say plus cosine, remember we're here, and I'm gonna use brackets like so. Let me use round brackets here now. Pi by 2 plus 0 minus x, and we're saying this is power 2025 dx. Now we're going to use a very special property. Let's simplify this first, taking us to page 4. Let's simplify this integral first. Simplifying this, what do we get? We get the following expression. I hope you can see it clearly. Yeah, you can. So simplifying this integral, we are basically saying that integral implies I is equal to the integral from 0 up to pi by 2. The top part is sine of, remember now, pi by 2 minus x to the power 2025 all over open bracket sine of pi by 2 minus x. Remember 0 plus pi by 2 is pi by 2. That's why I'm writing this expression like that. And we're saying power 2025, and then plus, we are talking about cosine now, cosine of pi by 2 minus x to the power 2025, and what do we have? We have dx. Now watch something very special here. What is special now is the property what we call cofunctions. Remember sine of pi by 2 minus theta equals cos theta, and cos pi by 2 minus theta equals sine theta, where theta is in radians. This is what you get. Special property. Now that expression therefore must become cosine. So now what do I have? What I have now is the integral from 0 up to pi by 2 of what? Of cos power 2025 of x all over. This part here is going to be cos power 2025 of x. Remember, this is what we're saying over here. If you have x there, that should be x, and if you have x there, that should be x. That's what is happening up here. And we're saying plus, this becomes sine of 2025 x, and what are we saying? Dx. Now look at what we've got now. A very simple and nice integral. This is I, but what is I initially? I initially is equal to this integral here. So what I'm going to do is to simply add the two integrals, add this to that. Remember, I equals this also. I equals this also. So therefore I'm going to say I plus I will be equal to, remember, I plus I must be equal to this integral plus that integral. So we're saying will be equal to the integral from 0 up to pi by 2 of which expression? This expression here. So we have sine of to the power 2025 of x all over sine to the power 2025 of x plus cos power 2025 of x dx plus, remember we're adding this, we added I and I, now we must add this and this, and something nice comes up. So we're taking this, adding there in front. So we're saying the integral from 0 up to pi by 2 of cos power 2025 of x all over, down here is cos 2025 of x plus sine 2025 of x dx. Now look at these two integrals very carefully. You'll notice that the denominator is the same here and there. This denominator is same as that. So what do you know when you have fractions that have the same denominator? Let me just remind you. If you have two fractions, for example, a over b plus c over b, what is the answer? We know that this is just b, and then we have a plus c. Right, so now we're going to have to add the numerators all over that, taking us to page 5, and just to finish this off now. So we are now saying those two integrals, let me move this one down. We're now saying those two integrals, this one and that one, on the left, obviously, you can see we have 2i. Let me put these papers in order so that I don't confuse you. All right, now, so on the left, we have 2i. On the right, we have the integral. Remember properties of integrals. Limits of integration are the same. So I can simply add these up. I want to remind you again that if you have the integral from a to b of f of x plus g of x or minus g of x, let me say plus or minus g of x dx, this is the same as the integral from a up to b of f of x dx plus or minus integral from a up to b of g of x dx. So therefore, if I have this, I can move back there. So if you look at these two, I'm like here, but with a plus sign. There's that plus sign there. So I'm moving back there. As long as limits of integration are the same, you're allowed to do that. Basically, we're saying the integration is linear, so to speak. So what are we saying? We're saying in the numerator now, I'm going to have that plus that. So we have sine integral from 0 up to pi by 4, sine power 2025 of x. My hand is misbehaving there. Power 2025 of x. That one there, you can see it. Yeah. Plus that. Plus cos power 2025 of x. We're dividing this by the denominator. What is the denominator? You can take this or that, it doesn't matter. Remember, here we start with sine, here we start with cos, but it's the same expression. A plus b same as b plus a. All right, so let's start with sine. Sine power 2025 of x plus cos power 2025 of x dx. What are we saying? You can clearly see that this works out very nicely. That cancels that. So what are we saying? 2i is equal to the integral from 0 up to pi by 4 of 1, because that's 1. 1 over 1 is 1 dx. Look at that. So 2i is actually equal to x. We're integrating from 0 up to pi by 4. So what are we saying? 2i equals pi by 4 minus 0, which is pi by 4. So what is our final solution? Therefore, it's actually pi by 2. My hand is misbehaving here. This is pi by 2 and I wrote pi by 4 there. I'm working ahead of myself here in terms of thinking. This is pi by 2. And that is pi by 2 and that should be pi by 2, and I'll fix this. That should also be pi by 2. I'm working ahead of myself there. That should be pi by 2, and therefore fixing this quickly, you agree with me that 2i equals pi by 2, and therefore I will just be equal to pi by 2 divided by 2, and our final solution is pi by 4. This is our final solution. So basically we are saying, if you allow me to move this to page 6, I'm coming to fix that one and that one. As you can see, we had here pi by 2 there. There is no reason why it should just change to pi by 4 suddenly there. My hand misbehaved there. All right, so let's just finish this off. So basically we are saying, to conclude this, we are saying, therefore, the integral from 0 up to pi by 2 of sine power 2025 of x all over sine power 2025 of x plus cos power 2025 of x dx, this is page 6, is just equal to pi by 4. Try this out and check and convince yourself that this is actually correct. Now look at how powerful the King's rule is. I normally don't call it the King's rule. I call it King's rule because there is only one the king. But yeah, that's a subject for another day. This is pi by 2, pi by 2, pi by 2, pi by 2, pi by 2. Right, so that is our final solution. This is how it goes. Now think about this, how powerful this is. Remember where we came from? This is where we started from. Looking at King's rule. I'm not going to go through this again. We've already gone through that, but this is how powerful this is. Evaluating that integral, looking very intimidating. Let me just show you this integral here, looking very intimidating. And by the way, I wanna explain to you something. I wanna say something to you. Even if you used power n there or any other number there, maybe even bigger than 2025, it should evaluate to the same value, because that's how it works out, by taking advantage of what we did here. Remember cofunctions. And I want to take you to that page. Here we go. Cofunctions there, and also the idea that when you rewrite this integral by using King's rule, you come up with the same integral. And therefore adding the two, it just gives you something very easy to work with. All right, I am going to stop here. Tell me what you think about this. Very involving, maybe one would say, but I think it's straightforward, not very difficult, especially if you use King's rule. Otherwise, there is no elementary technique that you can use to solve this one, except I don't know if you can use Feynman's technique on this one. I will try. I also invite you to try out using Feynman's technique, or the transition from rectangular coordinate system to polar coordinate system using the Jacobian. I don't know if it can work on this, but the powers are too big. So yeah, I'm going to stop here. Your feedback remains very critical, right? I'll see you next time.